Hi everyone. This series of videos is intended to introduce the Analog Discovery Board and the Waveform software. I'm Professor Ram from the Engineering Department at UMass Boston, and I also run the Ubiquitous Communications and Networking Lab, or UCAN Lab. In a previous video, we introduced the Waveforms WaveGen tool and the AD2 board's Waveform Generator channels. In this video, we will continue to observe analog signal generation with the WaveGen tool, but we will now introduce custom waveforms. Again, please note that you can find much more detail about these tools in the Digilant reference documentation at the link shown here. Coming back to our AD2 pinout, we will again be using the Waveform Generator channel 1 by connecting our W1 and ground pins to our circuit. In waveforms, we will again be using the WaveGen tool, but we will go into a bit more detail to show how to create more complex waveforms. When we open up our Waveforms software, we will again open the WaveGen tool. We've already explored some of the simple waveforms available within the Waveform software up here, but we actually have much more control, as we will see in this video. The first thing that we will do is look at a custom signal. In our drop-down menu here, we select Custom. We will use this to create our own arbitrary waveform, which will be repeatedly sent through the AD2's Waveform Generator. When we select New, we open up a window where we will be able to create our new custom waveform. There are a few ways to do this. And the left menu up here shows a few different options to generate our arbitrary waveform. Before we try any of these, we can actually start by just clicking in the preview window and dragging our mouse around to draw a waveform of interest. Let's draw a simple step down with 5 levels. We can see that as we drew this, the sample values in the right side here have been updated. Note that our sample values in this custom waveform are always going to be between -1 and 1. This is because we will eventually specify the voltage range with the amplitude and offset settings, just as we've done with our simple waveforms. The sample values shown in our custom waveform, the template here, are essentially normalized for a signal with amplitude of 1 volt and offset of 0 volts. If we want to make sure that we maximize this range, we can select Normalize, which will extend this waveform to the full range from -1 to 1, or -100% to 100%. When we click OK, we will see this window, or see that this now fits within the range of -1 volt to 1 volt in our actual signal preview. We can modify this by changing our amplitude to 2 volts and our offset to 3 volts, so that our signal now ranges from 1 volt to 5 volts. Let's now see what happens when we send this waveform to our AD2 board. Observing our AD2 hardware, we can see that we have a familiar setup with our 1 kilo ohm resistor in series with our LED. We have connected our W1 pin to the resistor and our ground pin to the cathode of our LED. When we come back to our Waveforms software and click Run, we notice that we see a constant brightness. The LED turns on, but we see this constant illumination or light output. This is, as we discussed in an earlier video, because our eye and my webcam only see the average brightness when the brightness changes at very high frequency. If we stop this waveform and change our frequency to 1 Hertz, we can then run again, and now we notice or observe, first we can observe that our time axes here in our sample waveform is a total period of 1 second. In other words, that the level actually changes every 0.2 seconds. as we run this LED, or as we run this on our actual LED, we can see the LED changing brightness levels. Now, drawing our custom waveform is great for getting a loose representation of the waveform of interest, but we usually want a more accurate representation. One way to do this is in our math operation, where we actually define the equation. So let's edit our waveform and see that in our math operation here we have our defaults set with 4096 samples over the range from 0 to 1. Our simple equation here uses the sine function and the random function. Since the value of x ranges from 0 to 1, the input to this sine function, 2 pi x, ranges from 0 to 2 pi. In other words, one full period of our sine wave. If we remove this additive random component and click Generate, we see that we get the full sine wave in our custom waveform preview. The random function actually creates a pseudo-random number with a uniform distribution between 0 and 1. And since our random function does not actually depend on x, we are just adding a unique random value to each one of those 4096 samples. Since we're multiplying this random value by 0.1, we actually get 4096 values all in the range of 0 to 0.1. If we remove this sine component and uncheck normalize in our bottom left, we can then generate the random component on its own. Now if we come back and add our sine wave back in and select generate again, we can see that the sine wave that originally ranged from -1 to 1, in other words from -100% to 100%, in our custom waveform preview, we have this sine wave plus this additional noise that ranges from 0 to 0.1. Therefore, our possible range of this signal is from -1 to 1.1. As you can see, the values above 1 fall above 100% in our preview and get cut off in this waveform. If we reselect normalize and then generate again, we can make sure that we get the full range of values assigned to this custom waveform. We can also manually enter values in our custom waveform generator. So let's first reset our custom waveform to a DC signal by clicking generate with this basic function. If we now select some sample, any one sample here, let's pick sample 1200 and change this to 0.7, we can actually see that it's updated in our preview. Again, we can set these values to anything between -1 and 1. But this would be a pretty tedious process if we actually want to manually enter all 4096 of these sample values here. So we can also see that we can set or we can enter a set of values in this value menu. If we define 10 values as seen here and select generate, we can see that each of these values is defined for approximately 10% of our waveform, or of our total time period. Note that as we normalized here, or we normalized this so that the values of 0 relate to -100%, and the value of 5, the peak value we've entered, relates to 100%. If we copy and paste these 10 values to create another repetition and giving us 20 total values, then we have 20 defined values that each occur for 1/20th of our period, or essentially 5%. Let's go back and delete these second set of values and regenerate and select save. If we want a little extra control, we can also go back to our simple menu, our simple controls, and now we should see that our custom waveform is available in this drop-down menu. Let's select this custom waveform and make sure our amplitude is 2 and our offset is 3 volts. So that again we have this range from 1 to 5 volts. In our simple waveform menu, we can come back and adjust our period to change our total period to 5 seconds. Now we can see that each of these on-off cycles takes approximately 1 second, since there are 5 total cycles in this waveform we've created, and each one occurs for about, or each value occurs for about 10% of that. If we run this on our 82 board, we can actually see the LED blink with increasing brightness. This just about wraps up our overview of the custom waveform option in our WaveForms WaveGen tool. Now, although we didn't discuss it here, you can also see that WaveGen has other options for things like play, where you can import and play audio files, or the sweep tool, where you can select a range of frequencies to sweep through and the amount of time over which the sweep occurs, going from that low frequency to that higher frequency signal. Well, we also have our modulation tool, where you can select a carrier frequency and a signal to be modulated, either using frequency modulation or amplitude modulation.